Hello, mentors. This is meeting 6, and this is part 1, and then investigations. So we have 4 different investigations. Students could pick either of these 4, create their own, or they could mix 2 of them. Let's see an example of how would that look like. So let's say they want to play with the inverse grid, where the vertices of the squares are actually the places where the shapes are put. And they also want to play absolute rule, when I'm happy when 2 or more or my neighbors are like me. Notice that they could change this parameter to 1 or 3 as well. So you have even more freedom than what it looks like here. But let's just have it with 2 or more neighbors that are like me. So how does the inverse grid work? Well, we actually have a 7x7 grid because we're going to place the shapes in these intersections, right? So you have 7 plus 7 plus 7, 7 times. So you have 49 different places. This would be an example, or where to place a shape, right? So all of these corners. And notice that a shape would have then up to 4 neighbors, which is little, right? Because in the normal grid, where you place the shape inside, you would have 8 neighbors tops. Here you have maximum 4, sometimes even 1 or 2 or 3. So let's pretend that this is the start state of the system. So somehow mixed. It could be more mixed, I think, but it's okay. Let's see what happens. And let's try to move shapes that are not happy. Of course, there's lots of shapes that are not happy, and try to place them in spots where they are happy. For example, this corner shape here only has 0 neighbors that are like this, like him. So he'll need to move. An easy place to move would be here. Now I'm happy, he would say. This triangle here is kind of as isolated, right? Only has neighbors that are not like that triangle, that them. So decides to move, maybe here. And so you see that you start creating some separation. Who else is sad? This square is pretty sad. And then finds a spot where it's pretty happy now. This is okay. This is sad, right? Only one neighbor. That's also a square. So move here. This is sad, unfortunately, and we'll move here. And then this will be sad, right? Because a neighbor just left. But okay, can move here. And so on. So let's do it a little more quick now, where I'm just trying to look for places where they move. And in reality, you don't consider all places, right? If you're going to move, but just the first or second of the good possibilities you have, right? Because this is time sensitive. So you, in reality, do it fast, this move. Anyways, starts to look like this. Uh, uh, I'm very sad still, so I'll just maybe wait. Okay, now I can move here and be happy. This is also sad, and I don't know how to fix it yet. Right, doesn't seem to right now. So let's keep looking. This is sad. Now it's happy, and then opens up for this triangle to be happy. This is also sad. Just one neighbor. I like. Now it's good. This is sad. Now it's happy, but now this is sad. Now it's still sad, so I cannot fix it yet. So yeah, you start to see that it's not so easy because you only have 4 neighbors tops and you want 2 of them 50% to be as you. So it's not even that the other neighbors are not like you, but that you don't have neighbors at all or few neighbors. So that's where the problem arises. Let's try to keep moving a little bit. Okay, now I'm better. So let's see what else can we do. Okay, we'll ask permission to this person. So the model may have a new rule that you can bump, right? That you can push and say, okay, I want you to maybe move a little bit, even if I'm not yet happy, just to try to create some happiness. So students could come up with this situation. Let's explore it like this shape here. Ask permission for this shape to move and moves it to another place. Still not happy this, but getting there. And then this would do the same for this shape. Stay so that they get happy. So the corners are important in a way. So what you could do is move here and here. And once you get a corner, this will be happy. And as long as you continue like this, so you go back to minify where you had lines, right? Of all homogeneous, all shapes being equal. But now this won't be happy. This is not happy either, so we could move it here as well. So it becomes, challenging, right? It looks easier, but it's very interesting actually. Move here. This is sad. Move here, at least to make this fellow neighbor happy. So another observation, as long as you have this line of 2, it looks solid because you'll get 2 neighbors each time, and it can end here. Doesn't matter that these shapes are here, because nevertheless, everybody here of the triangles will have 2 neighbors at least of the same type. So this type of configuration seems to work well. Here is a problem, right? We have a problem. Let's try to fix it in a way to exchange this. Let's analyze this square of triangles, right? So these configurations, it seems to work, so it's solid. So it becomes like chemistry, right? Where you recognize little molecules or little configurations that are stable, right? Because this has 2 shapes, same, and everybody's happy in this triangle, in this configuration of triangles. Who else has a problem? This shape, right? Not happy. Where could we move this shape? So we could first try here, maybe. Still not happy, right? Then we could try to move, or actually, move this one. Here we're good. We're good up to here. This is good. And then all of these are good. But now this is not happy. So we need to join these triangles probably here. This is not happy. Let's move it anyways, right? Let's see now. Let's check again, at least for the triangles, how happy or sad they are. So this is still a problem, right? Having just one fellow neighbor. So I'm gonna bump it here. And now we have this square of triangles, right? These 4 shapes that give me joy, stability for these triangles. And now, if I'm not mistaken, up to here, this region, everybody's happy for the triangles. But now this is a problem. If we move it here, I think we are good, right? 2 neighbors. So I think all triangles are happy, but of course, look at the separation, right? Look at the segregation that it caused, right? This square is not happy, but probably moving it here will make it happy. This is still a problem. So we could try to move it somewhere. And what we're gonna get is that we cannot put it anywhere and just fix the happiness, right? So what we'll do is, it's kind of a chain reaction, right? That you set up to get happiness, but you have to wait a little longer. Here, I think it's good. And so what we're gonna do, it's, yeah, again, like the chain reaction idea. This is now sad, right? Let's move it to here to get happiness. So again, we're creating segregation, right? We're moving to this big region. And then I'm gonna ask this shape to move here. Luckily, I don't damage the triangles. I think it's good because this is still happy, still has a good backup, right? As long as you belong to a square, right? You complete a square like this, a square configuration. That would be good. And then the same we'll do here. Okay, so almost all squares are happy now, except right for this one. And so I'll need to ask for permission, right, for these triangles. So maybe let's see what I can do. How about here, maybe? Okay, so now squares, the blue squares look good. They look happy. And again, every triangle belongs to this, to a block of 4, right? You can see. Well, except for, no, actually, yeah, all of them. That's good. Yeah, I guess except maybe this one, but still has 2 neighbors. So this is an interesting point in our model, right? In our state right now. Okay, take a look, take a few seconds now to convince yourself that every shape is happy. And it looks like so, right? But of course, we pay the price, right? And so we get a lot of separation, actually. Let's draw it out. Like really, really terrible separation. Like not even 3 or 4 clusters, but just very clear segregation, right? Which was natural, right? I mean, it was like shapes were going to be really sad, right? With these conditions, it meant to be hard to have only, I mean, you have 4 neighbors, tops, and 2 of them had to be like you. So half of them already started with this tolerance somehow. Okay, so hopefully that's good as a homework, optional homework. Try to do this again, but maybe with just one. So that'll be the end state, just with 1 or more neighbor. So change this parameter to only wanting 1 neighbor or more to be like you, and see what happens. See if you get less separation. Probably you will, depending on how you start. Let's end up looking at what happened, right? The movie. This start at the end. Look at this. All these simple rules, right? Okay, that's the video for now. See you in the next one and enjoy all this interesting modeling. Goodbye.